Welcome to this video on pH calculations. We're going to tackle here how you calculate the pH of a mixture of strong acids, and remember we're always with these videos looking at monobasic acids. So a mixture of strong acids, we've got HCl, a strong acid, and HNO3. These are both monobasic. How are we going to work out the pH? That's our final end goal. The pH of the solution is what we want to try and find, and we want to try and find that from this information that we've been given here. So pH is our goal. H plus ion concentration, as always, is our bridge into that, and this Sorensen formula is incredibly powerful. But now, when it's not quite so easy to go straight to the H plus ion concentration, even though we're going to carry on making our assumption that these acids are fully dissociated. So we've got here full dissociation, and so we're going to have this assumption that we can work out the H plus ion concentration is equal to the initial concentration of the acid. However, it's not quite so straightforward here because we've actually got two acids that we're dealing with. And so the key sort of stepping stone in these calculations is actually to recognize that we're going to need to work out the number of moles of H plus ions in total that are present. And then we can just use the formula concentration is number of moles divided by volume to get the concentration of H plus ions. Now, how are we going to get the H plus ion concentration in total? Well, we're going to recognize here that what we're going to get that from is the number of moles of H plus ions from acid 1 and the number of moles of H plus ions from the second acid. So if this is our HNO3 and that is our HCl, then we just need to add together the number of moles. You can't add the concentrations here because we've got different volumes of each of these. Moles is the best thing to sum up because it's just like counting a number. So we are going to go for full dissociation, which is going to allow us to make this equivalence here. So the number of moles of HA is equal to the number of moles of H plus. So in fact, it might be helpful to have that way of writing the formula actually noted here, just to remind you. So initial moles of HA is equal to the initial moles of H plus ions. So that is going to be how we work this through. So let's actually do that. So the number of moles of H plus that's coming from the HCl is equal to concentration times volume. So I'm saying that I'm just going for the concentration of that, which is 0.5, and I'm multiplying that by the volume, which is in centimeters cubed. I want to turn that into decimeters cubed, and so I'm going to multiply by 10 to the minus 3 there. I'm going to find out that this is 0.0125 moles. The number of moles of H plus ions from HNO3 is going to be a little bit bigger because we've got more of it and it's a higher concentration, but again it's concentration times volume. 2 is the concentration. The volume this time is 75 times 10 to the minus 3, which is going to come out at 0.15 moles. Then we work out the number of moles in total, which is just adding these guys together, so it's going to be 0.1625 moles. The concentration of H plus is just number of moles divided by volume, which is going to come out in this case at 1.625. So now we're on our last stepping stone. We just stick that in the Sorensen formula. Minus log base 10 of that turns out to be minus 0.21, at least to 2 decimal places, which is the most common for pH. So mixtures of strong acids, you're going to be using this kind of relationship here, where the total, you're going to be working out the total number of H plus ions, total number of moles of H plus ions, by adding together the number of moles of H plus ions from the two species, and making this time the assumption is the same, but perhaps it's more useful in this form, which is the number of moles of H plus ions is equal to the number of moles of acid molecules that you start off with.